which starts the topic about moments, the moment of a force. And what I'm going to do is talk to you to start with about two examples. One of them is if you had a wheel, and I'm not sure whether any of you have done this, but if you've got a wheel on a car with bolts on and you're trying to undo the bolts, then of course you're going to use a, a very badly drawn spanner to undo that nut. Now, how do you, let's imagine it's a really tough nut and you're not quite sure, and you want to try and undo it, sorry, then how are you going to do this? Well, there are two ways in which you can try and increase your chances of undoing this. Of course, you'll be putting a certain force on the nut, and you can increase the size of that force, and hopefully the nut will undo. Or the second thing you can do, of course, is increase the length of the arm of the spanner you're using, and then use that same force, that maximum force, at a greater distance. And then those two coupled together means there's more chance of undoing the nut. You might see, if you've seen people changing their wheels before, they're standing on the spanner, hence they're increasing the force, or you might see them put a little extra arm on the spanner as well to increase the distance. So if we were to define them, and essentially what we're doing is, that is increasing the moment of the force. So if I had to define a moment of a force for you, it's the turning effect. So we'd say the moment is equal to the force times the distance. And I'm writing that slightly lower because I want you to think about the second example I've got. So in the second instance, I'm sure you've all ridden your bikes, and when you ride your bike, you'll notice that there is a different ease of turning the pedals when they're in these three different orientations. Okay. Now, let's imagine you're still exerting the same force down on the pedal, so you're pushing as hard as you can down. And the question is, why is one position more easier to turn than the other? First of all, we need to know about which position is easiest to turn, and I think intuitively you'll probably know that's this position here, so this is the easiest. Whereas this position here is the hardest. However, if we're talking about moments, then you can say to yourself, well, actually, I've got the same distance in each of these three examples, and I'm exerting the same force in each of these three examples, so therefore there should be the same ease of turning the bike pedals around. Well, that's not actually the case because, and this is what I'd like you to remember when you're thinking about this, it's not technically the distance we're interested in. We're interested in the perpendicular distance. The perpendicular distance. In this example here, it is the greatest distance, so therefore it's creating the greatest moment. In this example, though it's the same length of crank, the perpendicular distance has decreased quite considerably, so therefore the moment has decreased. And in this one here, there is absolutely no perpendicular distance, and so therefore, irrespective of how hard you're pushing, if the perpendicular distance is zero, the moment is zero. And you probably noticed if you're on your bike like that, you can actually stand upright on it. So what we really ought to write here is the perpendicular distance. It's a subtle point, but a really important one. Now, if you can remember that, of course, I just write it formulaically as that, with our units as newtons, meters, and so therefore our moment must be a Newton meter. You might be given lengths in different units, but try and keep it to meters all the time, and definitely in newtons, so a Newton meter. And also a moment comes with an associated direction, and so we can either call it anti-clockwise, clockwise, or clockwise moments. So it comes with a direction. Excellent. Okay, let's try some very, very simple examples to start with, so we're familiar with how this is calculated. Often triangles refer to pivots, and a pivot is the point at which something turns around. And very simply, if I have my first example, I have, let's say, 5 newtons, and this is sitting at 3 meters away from my pivot, then my moment is going to be the force times the distance. 5 newtons times 3 meters, giving me 15 newton meters. Okay, very straightforward. To be absolutely rigorous with this, I need to give it a direction as well, so I'm going to call this one is going to be clockwise. Okay, another brief example. Let's try and use similar situations, but this time I'm going to change the direction of the force. And so though it looks identical length, let's just say this is 20 centimeters. The moment of my force is again force times the distance. 2 newtons times 20, 0.2 meters, giving me 0.4 newton meters. However, this time, sorry, that's meant to be in newton meters. However, this time it's anti-clockwise. I suppose in the second example, I quite like to put the double arrow to indicate what's happening. And obviously in the first example, it's acting downward. Okay, really straightforward. I don't think you're going to have any trouble with that at all. However, there's the moments get really useful when you end up balancing moments, and you can consider moments on two sides and like a seesaw in effect. So we're going to look at now at balancing moments. Or the seesaw. So let's look at a very simple example. This time now, around the pivot, we have 2 forces acting at different positions. Let's just say arbitrarily. We've got something acting at 3 meters and something acting at 1 meter. And I'm going to make this a 10 newton force, and on this side what you'll always be presented with is you'll be presented with an unknown. And you have to work out what the unknown force will balance what the value of this in order for this to balance. So essentially the big idea is that the anti-clockwise moment must equal the clockwise moment. And if that is the case, then this means that we have a balancing. Something will be balancing. Of course, if this is not the case, then one side will start to move. If you have a moment, it creates a movement. Only when they're equal will we have this situation balancing. So all you would do is you would set up this situation. You would work out the moments on anti-clockwise and the moments clockwise and see what happens. So let's work out to start with the anti-clockwise moment, which is the force times the distance again. In this case, it's an unknown force. Let's call it F rather than a question mark, times 3 meters. And that must equal the force times the distance, which is, let's write that a bit higher, 10 times 1. So therefore, the unknown force in this instance is going to be 10 times 1 divided by 3, giving me a terrible choice of numbers, because then I end up with this repeating decimal, 3.33 newtons. Now, I'm sure you intuitively know that anyway, because the further you are away from the pivot point, the lighter the force, the less the force required to support a weight. So in that this is 3 times further away, implies that it's a third of the force available to it. Superb. Right, next one. Let's just try and make this slightly harder, because this can be applied to quite complicated systems. Let me, and I'm going to try some arbitrary figures again, so this could give rise to some terrible numbers. It doesn't just need to be one weight. you could have multiple weights on one side at different positions. And that could be supported just by one large weight on the other side. So let's say I have values of, let's say, 20 newtons. Let's have 40 newtons. I've got, let's say, half a metre and another half a metre, separating the two masses out. This one I'm going to place at 2 metres, so therefore what force is needed in order for this situation to balance? Well, imagine that pivot point is where it's all acting about, so therefore let's work out the moment on both sides. Of course, if the moment is force times distance, then we have an unknown force, F, multiplied by the 2, and that gives us just merely the sum of these two moments. So let's deal with the first one, 40 times 0.5. And now 20 times, now be careful here, it's 0.5 that separates, so therefore it must be 1 metre from the pivot point. So you must calculate it from the pivot. So what does that give us? That gives us 20 plus 20, giving us 40. And so F in this case is going to be 40 divided by 2, which gives us 20 newtons. So in order for this situation to balance, that must be 20 newtons of weight onto it. Good. Shall I give you a question to try now? Another really arbitrary one. See how well you feel you understand this. And I will make it a complicated system for you, because I think this should be quite straightforward. Let's have two weights. One acting at 0.75 of a metre, one acting at 50 centimetres from that. We're going to have a 2 Newton and a 3 Newton force. And on the other side, I want 5 newtons and an unknown distance. So if you think you can do that, then give it a go. Hit pause. Otherwise, I'm going to go for the solution right now. Okay then, on the left-hand side, it's fairly straightforward. Remember, bearing in mind the force times the distance is going to give us our moment. And so therefore, 5d, on the left-hand side, 5 times the distance, is going to give us 2 times 0.75, force times distance. Added to that, now you're going to have to do a little bit of conversion here. If that's 0.75 and this is half a metre, that gives us 1.25 metres times, from the pivot of course, times 3. So we can we can work out the sum on the right hand side. This is going to give us 1.5, and add to that it's going to give us 3.75. Of course that's going to be 5 lots of d, so if we divide this by 5, that will give us the distance. So a nice, easy, straightforward question there. It's going to lead us to 5.25 divided by 5, which will give us 1.05 meters. I'll just double check that. Yes. So 1.05 meters. Now, so I suppose that probably makes intuitive sense. You've got 3 sitting at 1.25, you've got 2 extra, so this is going to be a little bit further than you'd normally expect it to, because they've got 2 weights. Fantastic. Now, I think there's just one last type of problem we need to show you, and that is if we're dealing with bridges. Okay, I'm sure you're familiar with the structure of a bridge. This time, rather than having the pivot in the middle, in effect you have two supports on either side. You have a force acting on one side of this bank, let's imagine this is a river it's going over, and a force acting on the other side. And you might have, say, a weight acting at some distance between this bridge. So let's make these figures arbitrary again. Let's say this bridge is 10 meters wide. This one is sitting at 2 meters. Oops, that's not 2 newtons, 2 meters, and it has a 50 Newton force on it. You can then quite successfully work out the force that this side support has to provide and this side support has to provide. And I will show you how you do it right now. I'm just going to have to move on across to another bit of paper. This might be a bit tricky. Hold on, let me see if I can leave that in shot. Right, so what you do is, the technique is, first of all, number one, you take one of the supports as the pivot. So we assume that one of those is the pivot. Second idea is then you work out the moments, then you balance the moments. Third point, you work out the unknown. Okay, so let's assume that this point is the pivot. We have, acting around that, first of all, we have 2 meters and 50 newtons acting. And then adding to that, we have 10 meters by an unknown, we do have a distance, sorry, by an unknown force. Let's call it force Fn. This is obviously a anti-clockwise moment, so really we should write that as a minus. And this is a clockwise moment, so that's a plus. And obviously both of them must equal 0. Or if you prefer, you could say that the anti-clockwise, and just write that on this side, must equal the clockwise. And you can write that on the other side of the equation. So really think of one side of the equation as anti-clockwise, the other side is clockwise. Or if you prefer and you like working from a pivot point, obviously no movement occurs here, therefore you have to place it all on one side, but bear in mind that negative number. Anyhow, the force is going to be the 100 divided by the 10, which means it's 10 newtons. It's experiencing 10 newtons of force at this side. Now, with really, I mean, intuitively, you should understand then that what's the force on this side, x, just arbitrarily? Well, the force at x, well, because you're only supporting 50 newtons, it's just going to be the remainder of the force that's not acting on the other side, 40 newtons, which is the quick method. Or if you want to try and make this a lot more long-winded, when we can work out, we can imagine the pivots on the other side, and we can say to ourselves, well, what we will do is we will balance the forces again and see what happens. We can now we know this is, now we can say slight difference here, because you're going to have to consider this distance to the edge from the pivot, because the pivot has changed. That would be 8 meters. So therefore we say 8 times 50 newtons, which is our clockwise moment, minus our anti-clockwise moment, which is Fx, times our 10 meters, or if you're acting, if you'd like to write all on one side and the other, f of x is going to be 8 times 50 over 10, 400 over 10, giving us 40 newtons. So either way is just as acceptable as whichever. Right, okay then. Here we go. I'm going to set one more example, and then I'm going to let you have a go at it. Let's have a bridge again. acting across some water. Place an object at, let's say the span here is 20 meters. This is acting at 1 meter, and it's a 100 Newton weight that is sitting on the bridge at that point. Could you work out the force M, arbitrarily, I don't know why I chose M, and the force at B? Okay, hit pause and give it a go, otherwise watch the solution now. We're going to imagine that is acting as the pivot for situation 1, so let's do the first pivot point. I'm going to say that the clockwise 1 times 100, and it's anti-clockwise, so I'm minusing it, 20 times Fm is equal to 0. Fm is therefore going to be 100 divided by 20, giving me 5 newtons. If I imagine the other side, then I can say 0 equals my anti-clockwise. Now let's go with my clockwise first. My clockwise, which is clockwise is going to be Fb times my 20 meters minus the 100 multiplied by, careful here, 19 meters, because this is 19 meters. And so, oh goodness, I was expecting it to be easy in that in my head. So Fb is going to be 100 times the 19 divided by 20, giving us, and the reason I can work that out fairly quickly in my head is because, let me just work it out first, it's 95 newtons. The reason why I know that's because if I did it the quick method, I would know that my 100 newtons totally has 5 newtons acting on one side of the bridge, so therefore 95 newtons must be acting on the other side. Okay, that's absolutely brilliant. I suppose there's one point I will leave you with, which we'll deal in the next video, and that is if I had a beam and I placed the pivot in the middle, directly in the middle, it stays balanced because I've got equal amount of weights on either side. If, however, I move the beam to the side, why does this side fall over? I'm going to leave you with that question, and you can see the answer in the next video.